This video is an introduction to the regression, correlation, and hypothesis testing chapter. We're going to be looking at exponential models here. Now, regression lines are used to model linear relationships between two variables. A regression line is really just a line of best fit. So when we've got two different types of data and we put them on a scatter graph and try to draw a line of best fit, if we can draw a good line, then there's a linear relationship between the two variables. So linear meaning a straight line relationship. So not curved, has to be a straight line. However, when bivariate data is not linear, so the relationship could be curved, we use logarithms and coding to look for trends. Case number one is data that can be modeled by a relationship of the form y equals a times x to the power n, where a and n are both constants. So we start with y equals ax to the n. What I'm going to do now is derive the regression equation. Take logs of both sides. I've chosen to use log base 10. So if you see log without a base, it means log base 10. So logs of both sides. Before I go into the next line, don't make the common mistake here of thinking that log of a times x to the power n becomes n log ax. It doesn't. This is wrong. Here, the whole of ax to the power n is being logged, not just the ax. So if we had this instead, log of ax in brackets to the power n, if we had that instead, then yeah, that could become n times log of ax. So make sure you don't make this mistake. After taking logs of both sides, use the multiplication law on the right hand side to get log a plus log of x to the power n. Now we can use the index law on log of x to the power n, which becomes n log x. So now if we have this relationship, y equals a times x to the power n for the original data, where a and n are constants, then we can get this straight line relationship. I've just compared this with the equation of a straight line, y equals mx plus c. I'm just going to use capital Y, capital X to avoid confusion with this y and this x. So y equals, I'm going to write it the other way around. Instead of putting mx plus c, I'm going to put c plus x. So here, instead of log of small y, we've got capital Y. Instead of log of small x, we've got capital X. But everything else are constants. So log a and c, they're both constants. N and m are both constants. So this does fit the equation of a straight line, where n is the gradient of that line and log a is the y-intercept. Like I said, n is the gradient because that corresponds with m, and log a is the y-intercept. That's case number one. Case number two is data that can be modeled by this relationship, y equals k times b to the power x. Note the difference with the previous one. The previous one was y equals ax to the power n. Now x is in the power this time. Same process, start with the model, log both sides. On the right hand side, do not make the common mistake of turning this into x times log of kb. Don't do it, it's wrong. The thing you should do, the right hand side, use the multiplication law to get log k plus log of b to the power x. Now we can use the index law on log of b to the power x. So to summarize, if we have this model, y equals k times b to the power x, once again k and b are constants, then we get this form. So comparing this, like I did on the previous slide, with the equation of a straight line, so y equals mx plus c, just written in a slightly different order. Instead of log y, we have capital Y. And this time it's a more straightforward swap. Instead of small x, we've got capital X. So this does fit the equation of a straight line. And by comparing, we can see that the gradient must be log b. So m, which is the gradient, is log b. And the y-intercept is log k.